A warm greetings from Erode Sengunthar Engineering College, Erode, Tamil Nadu. This is an GATE coaching program for SCSU students applying higher education under AICTE PRERANA scheme. Right? I am G.Lingeswaran, Assistant Professor in ECE department. Now I am going to handle the session digital circuits. Session analog to digital and digital to analog converters. Right? In our regular life, most of the real world physical quantities such as voltage, current, temperature, pressure, time, speed, velocity, we are measuring. These signals are available in analog form. And the analog signal represents a real physical parameter with very good accuracy, but it is difficult to process. Right, to store or transmit the analog signal without introducing considerable error because of superimposition of noise, as in the case of AM, that is amplitude modulation. In AM, noise is the very big problem. For processing, transmission and storage purpose, it is often too convenient express these variables in digital form. Right. So basic difference between analog form and digital form. Analog form means simple example. Sine wave is the example of analog form. Digital form means it is it is available in logic 0 and logic 1. Right. In digital signals, it gives better accuracy and reduces noise. The operation of any digital communication systems based upon the analog to digital and digital to analog conversion. Right. So this is this diagram shows the basic DAC techniques. Right. So here how we convert the digital signals into analog signals. Right. For example, here we are giving the input signals. This is a circuit called 8-bit DAC. This circuit accepts the 8 digital input signals named as D0, D1, D2, D3, D4, D5, D6 and D7. Right? We are applying 8 input digital signals. Then we get an output in analog form. Right. So output, how what's the equation to get output form? Output voltage VO is equal to K into VFS into D1 into 2 power minus 1 plus D2 into 2 power minus 2 plus D3 into 2 power minus 3 and up to n number of bits, Dn into 2 power minus n. Here VO is the output voltage. VO is the output voltage, that's called analog voltage. Right? VFS means full scale output voltage, where K is the scaling factor. Then D1, D2, D3 and Dn are the n bit fractional weight input applied digital bits D1 to Dn. And there are 3 types of converter circuits, digital to analog converters. First one, weighted resistor type. Second one, R2 or ladder type. Third one, inverted R2 or ladder type. Next, let us see the operation of all these 3 types. Here, this diagram shows the weighted resistor type D2A converters. This is a n for n bits implementation. So this is a circuit for converting digital signals into analog signals DTA. We use an amplifiers. We are using an amplifier circuit, operational amplifiers. IC 741. Here we give the input signals to the inverting terminal. Inverting terminal feedback is the RF is equal to R by 2. This is a feedback resistance. Right. Here this is the reference. This is the reference signal V reference we are giving. Then here it represents the 1, 2. This represents the switch S1, S2, S3 and Sn are the switches. It means 1 means ground. It is connected, 2 means it is logic high. So logic Y high or logic, it means 1 means ground, 0 signal. Otherwise, if it is connected to 2 means reference signal is connected to the inverting terminal. Similarly for S2, S3 and Sn. Right. So output voltage VO is equal to minus I into RF. Right. So minus I into RF is the feedback resistance value. So output voltage is equal to minus I. The value of I is given by I1 plus I2 plus I3 plus up to IN, because we have n number of branches. R, 2R, 4R. So it switches S1, S2, S3 and up to Sn, for so that we represent I1, I2, I3 and so on up to In into RF. So we can take output voltage is equal to minus, how to calculate I means VR divided by 2 power 1 into R into B1. B1 is the bit position, whether it is 0 or 1, logic 0 or logic 1. So for second bit B2 into VR divided by 2 square into R plus B3 into VR divided by 2 power 3 into R plus up to so on up to Bn into VR divided by 2 power n number of bits into RF. Simplification, we get V0 is equal to minus RF by R into VR is common, we take outside. So B1 into 2 power minus 1 plus B2 into 2 power minus 2 plus B3 into 2 power minus 3 plus and so on up to Bn into 2 power minus 1. If RF is equal to R, if we consider feedback resistance value equal to input resistance value R, we can take finally we get output voltage VO is equal to minus VR into B1 into 2 power minus 1, B2 into 2 power minus 2, B2 into 2 power minus 3 plus so on up to Bn into 2 power minus 1. Here B1 represents the B1, B2, B3 represents the digital bit values 1 and zeros. Right. So this is a second type, R2R ladder type. Right. R2R ladder type. This is example of R2R non-inverting ladder type. Here we use the two resistor values. In series form we connect to the R value. In parallel form we connect to the 2R value. Why? Because in the previous method we use the R2R 4R. For example, if we increase the number of bits value, for a first bit we use the R value, R resistance. For a second bit we use the 2R resistance. For example, R means first value if we take 100 ohms means for 2R it becomes 200. Similarly, 4R means 400. For 5R means it is 500. Similarly, 5 then 8R then 16R, 32R. So if we increase the number of bits up to 32 bits or 64 bits, then it means 64 into R, 64R. So it is practically difficult. It is practically difficult to get the value of resistance. So we choose R and 2R value. Here we use the only two resistance values R and 2R. Right? So R value in series arm we connect only R. In parallel arms we connect 2R resistance. Right? So we connect the reference voltage. Right? The reference voltage plus 5 or plus 10 volt. It indicates the logic 0 or logic 1 value. If the switch position is connected to ground means it is 0. If switch position connected to reference means it indicates the input is 1 signal. Right. So this is the R2R non-inverting terminal. The input signal is connected to the non-inverting terminal plus of the operation amplifier. Right. So this is the output equation. VO is equal to V reference divided by 2 power n into summation of I is equal to 1 0 to n minus 1 to I 2 power I into BI number of bits into 1 plus RF by R1. This is the output equation for R2R ladder type. Then this diagram shows the inverted R2R. Right? Here we give the input signal to the inverting terminal of the operation amplifier. Right? Here also we take the resistance value R2R. The current flow value I by 2, I by 4, I by 8, I by 16. This is an analog signal. Right. So this is the conversion equation. V out is equal to minus V reference into B3 into 1 by 2 plus B2 into 1 by 4 plus B1 into 1 by 8 plus B0 into 1 by 16. For example, this is for 4-bit combinations. 4-bit combinations. So 4 bits 2 per 4 16. So 16 means here for B0 2 per we add 16. Then B1 8, B2 4, then B3 2. This is for 4-bit R2R. For a general n-bit R2R ladder network, final output equation VO is equal to minus V reference into summation of I is equal to 1 to n B n minus 1 n minus I into 1 by 2 power I. Right. Next one, analog to digital converters. Right. It provides the function just opposite to that of digital to analog converters. Right. It accepts the analog input signal VA and produces a binary output form D1, D2, D3, and so on up to DN. Right. Here in the analog to digital conversion process, there are two basic steps. Right. Here, first one quantizing, second one encoding. Quantizing means breaking down analog voltage into set of finite states. Encoding means assigning a digital weight or number to each state. These are the two-step process. Right. So this is the basic functional diagram of analog to digital conversion. Right. For example, this is an example circuit. Here we give the sine signal, analog signal, input signal we are giving, that is applied to the sample and hold circuit. It is controlled by the control voltage. Then that is given to the quantizing and encoding. Finally, it gives an digital output signals D0, D0, D1, D2 up to Dn. So here we convert the sine wave into sampling. We do a sampling process. Next, I will explain the sampling after the types of operation. Then there are main two types of ADC circuits. First one, direct type ADC circuit. Second one, indirect type ADC circuit. In first direct type ADC, it compare a given analog signal with the internally generated equivalent signal. There are four subtypes. First one, flash type or comparator type. B, counter type. Then C, tracking or servo type. D, SAR type. These are the direct type of A to D converters. Then second classification, it performs in an indirect manner by first changing the analog input signal to a linear function of time frequency and then to digital code. There are two types of indirect type ADC circuits. First one, charge balance type, and second one, dual balance type. First one, flash type analog to digital converters. Flash, it is a more expensive one. It is a single cycle, uses many comparators in parallel with different references voltage. Right. So this is the basic diagram. We are giving analog signals. Analog signals are given to the comparator circuits. N number of comparators we are using. Also, comparator, another input is the reference voltage VR1, VR2, and VR N. VR N up to VR N. Then comparator circuit compares the input voltage. Then based on the value, based on the analog value, reference value, compares, it gives the output value either 1 or 0. Then these signals are given to the digital circuits, digital logic circuits. Then we get a digital signals bit 1, bit 2, up to n number of bits. Right here, 2 power n minus 1 is the comparator for n bits. If you want to take n bits output, if you want to take n number of outputs, we have to use 2 power n minus 1. For example, if you want to use 8-bit outputs, you have to use 2 power 8 minus 1, which compares we have to use. Right. So each reference voltage equivalent to quantization level. Encoding logic produces a final weight. Right. How the flash works? As the analog input voltage exceeds the reference voltage, at each comparator, the comparator output will sequentially saturate to a high state. It means logic high. When analog input voltage exceeds the reference voltage VR at each comparator, the comparator output will sequentially saturate to high state. It means logic 1. When the analog voltage is less compared to reference voltage, output voltage is equal to 0 of the comparator. The priority encoder generates a binary number based on a highest order of active input, ignoring all other active input signals. Right. So next one is the counter type ADC circuit. This is the basic block diagram of counter type circuit. Here we give the analog voltage to the comparator. Then comparator we give the reference voltage. then control logic. It is control output of comparator is given to the control logic. Then control logic is controlled by the clock circuit. When the clock signal is high, the signal from the comparator is passed on to the counter. Based on the number of ones or zeros received, it counter circuits gives an output. Then that is given to the digital to analog converters. Here we give the analog reference voltage. For example, analog signals. For example, for each counting, we get the step value 111. We get the step value, and this is the form analog signal. This is a here we are giving a given analog signal. For analog signal, then it is given to the comparator. Control voltage comparator output given to the control logic, then it is controlled by the clock signal. Then control logic signals output is given to the counter. The counter circuits counts the values and given to the digital to analog converter. So here we take the analog. It means already I mentioned that in this type, it compare the given analog signal with the internally generated equivalent signals. This is the example. Internally generated signal is converted, taken as a reference signal, analog form. Clear? Right. Next one is the servo tracking type analog to digital converters. Here also, here the clock signal is given to the up and down counter. Also, comparator circuit we give analog signals. Then based on the clock signal, based on the comparator output is given to the counter circuits. Then these signals gives the correct digital output value. Then these signals are converted into analog signals as a reference voltage VDAC. For applied digital for digital signals, analog voltage is given to the comparator in negative terminal. This is called servo tracking type ADC. Next one is the SAR type ADC. It is means successive approximation register type analog to digital converters. For example, here the 8-bit SAR, here we give the input clock signals, then 8-bit DAC circuit, it gives the analog signals that is given to the comparator internally generated. Here we give the signal which is to be converted. That is the analog input signals to the comparator. The comparator output is given to the 8-bit SAR. In the 8-bit SAR type, in this method, how the signal is converted means, for example, it compares the previous one value. It means, for example, it compares the previous one value based on the previous value. If the previous value, and for example, initially the all outputs are 0. Initially, all outputs are 0. Then for this 0 digital signals, converted signals given to the analog signals. Then comparison, if the voltage is high means, then it sets the LSB to 1 value. Otherwise, then it is signals converted into analog signals. Then similarly, for this digital signal, this given to a comparator circuit. Again, comparator circuit gives the signal serial data to the input. Again, it converts into digital output. We get, again it compares the compares the value. For after comparison, if the value is high means it sets the near to the value 1. Otherwise, it makes already previous value high, that is makes to 0, then it makes high to the next to the LSB bit. This is the process, successive approximation. Like this, the entire process is completed. Right. Next one is the real slope analog to digital converter. So this is the circuit diagram. It's for the dual slope type. Here we give the for comparator, we give the analog signals V in and V reference. Right. Alternatively, we give the two signals V in and V reference, that is given to the inverting terminal. Then that is given to the operation amplifier. Then operation amplifier, the signal is given to the control circuit, control logic. Then it is controlled by the clock circuit. The counter circuit counts the number of ones and zeros from this operation amplifier. Right. So for this, we give two signals V in and V reference. Right. So next one is the sample and hold circuit. So this is an important concept in an analog to digital and analog to digital conversion process, sample and hold circuit, right? Operation here, A1 and A2 are acting as a voltage follower circuits, right? So the main use of sample and hold circuit is then to sample the input signals and holds on to lost sample value until input is sampled again. This is the basic process, right? So sample and hold circuit, it samples the input signal and holds on to its last sampled value until the input signal is sampled again. It means for we converting analog signals into digital signals, we cannot take all the entire signals. For this, we take the sample of signals only for particular time interval. For example, every 5 seconds or every 10 seconds. During the duration, we take the analog signal. That analog signal is converted into digital signals, discrete. Then this value is converted into considered for converting and the analog signals to digital signals, right? So this is type of circuit is very useful in digital interfacing, analog to digital and pulse code modulation systems. The N channel in the circuit, here the A1 is acting as a voltage follower, A2 is voltage acting as also voltage follower. VI input signal is given to the A1. Here the sample and hold control voltage is given to the MOSFET, E MOSFET. Then that is controlled by, that is given to the holding capacitor. This capacitor determines the timing, and it is given to the A2. Here this is a simply voltage follower circuits. Two voltage followers are connected in series form through MOSFET and capacitor. The N-channel E MOSFET works as a switch and it is controlled by sample and hold SH control. It means controlled voltage, and the capacitor C stores the charge. Right here, VA is the analog input signal. VA is the analog input signal and applied to the drain of an E MOSFET. Operation: when S and H control is positive, E MOSFET turns on and capacitor C charges to VI. Clear? Then the output appears at A2. The whatever input signal available, that is appeared at the output of voltage follower 2. Then when SH control is 0, E MOSFET is off. Now the C is facing high impedance state of the voltage follower A2 and cannot discharge. So the capacitor holds the voltage across it. Whatever the sampled value, it holds the value. Right. So where here Ts is taken as a sample period, Th is considered as a holding period. So Ts means sample period, at which time, which duration we are taking the samples. Holding time, at which time, how much time we are holding the, it means capacitance charging time. The frequency of the S and H control voltage should be kept is twice than that of input signal. This is a main condition. Right. So this diagram shows the input and output waveforms of the sample and hold circuit. Here the green curve wave, this shows the signals to be sampled, input analog signal that is given to the sample and hold circuit. Then based on the command signals are digital signals, logic 0 and logic 1, train of pulses. When the train of pulses are high, the MOSFET transistor on. At the time, what are the input available analog value that is available at the output side. So this is the analog value. See, this is this type of waveform we get. This gives the sample and hold circuit output. So continuously we are not taking the samples, we are taking the signals. At a particular time interval, we take an analog signal, then that is converted into digital signals. Clear? Okay. Next one, droop rate. So this is the another one parameter, important parameter in this sample to hold circuit. The droop rate is the downward slope of the top of the output voltage pulse resulting from a flat top current into pulses. Means time taken to uh, give the flat top downward slope of the top of the output voltage pulse resulting from flat top current to input pulse. Right. Next, we see the some example problems asked in the uh, gate exams, previous years gate exams. Right. So first problem, express the output voltage of digital to analog converter. For example, this is for example, four options given. VO is equal to K into VFS into D1 into 2 power minus 1 plus D2 into 2 power minus 2 plus D and so on Dn into 2 power n 2 power minus n. Similarly, VO is equal to VFS by K into this term. VO is equal to VFS into this term. VO is equal to K into D1 into T2 2 power minus 1 plus D2 into 2 power minus 2 plus Dn 2 power minus n. Right. So correct answer is option E. The input signal is an n-bit binary weight, and D is the combined with the reference voltage VR to give an analog signal output signals mathematically described as VO is equal to K into VFS into D1 into 2 power minus 1 plus D2 into 2 power minus 2 plus Dn into 2 power minus n, where K is the scaling factor, VFS is the full scale output voltage. Right. Second one, determine the output current for an n-bit weighted resistor DAC. Right. Here are four options: VR by R into DO by 2 plus D1 by 2 power 2 plus Dn by 2 power n. Option B, VR by R into D1 into 2 power 1 plus D2 into 2 power 2 plus Dn into 2 power n. Option C, VR by R into 2 into D0 power 2 by 2 plus D1 square by 2 square plus Dn square by 2 power n. Option D, VR into R into 2 D0 square by 2 plus D1 square by 2 square plus Dn square by 2 power n. Here the option is, answer is B. Explanation: the output current is given by IO is equal to I1 plus I2 plus up to IN. So IO is equal to, we can write I1 is equal to VR by 2R into D1 plus I2 is equal to VR by 2 power 2 square into R into D2. For I3, we and so on up to n number of bits VR by 2 power n into R multiplied by Dn. Right. So we simplify, after simplification we get IO output current is equal to VR by R into D1 power 2 power 1 plus D2 into D2 by 2 square plus Dn by 2 power n. Next. Third problem, determine the full scale output voltage in an 8-bit DAC for 0 to 15 volt range. Right. This is a given problem. Options are full scale output voltage 15.1 volt, 15.2, 14.5, 14.94. Here option is D. Explanation: full scale output voltage is equal to full scale voltage minus LSB. Right. So LSB, so here full scale output voltage is 15 volt minus 15 volt divided by 2 power minus 8. So it gives the value of 14.94. Next, problem number 4. The smallest resistor in a 12-bit weighted resistor DAC is 2.5 kilo ohm. What will be the largest resistance value? Right. So it is that earlier I mentioned a drawback of weighted resistor type. It is a smallest value is 2.5 k. For then the largest value is 12.2 power n into r. So here n indicates the 12. So 2 power 12 into 2.5 is that is equal to 4096 into 2.5 k. The answer is 10.24 mega ohms. So this is for 12 bit. Next, fifth one, for a given circuit, find the output voltage. So this is a circuit diagram given. We have to find the output voltage. right? So answer option A minus 5.625 by 3.50, 4.3 minus 4.375 minus 3.125. Answer is D. Explanation for the given circuit. To identify, first we have to identify the which type of circuit is, right? So the given circuit is a 4-bit R to R digital to analog converters, right? So first we have to identify the type of circuit, then we have to write the formula, then we have to apply the values, right? So output voltage is equal to VO is equal to minus RF into B3 by 2R plus B2 by 4R. Why B2 B1 means because B2 here the signals B3 then B2 are connected in uh, connected to the one remaining are 0. So 0 into 0 value is 0. We take the signals which are connected to the 1. So we get the value B3 is equal to 5 volt, B2 is equal to 0 volt, B1 is equal to 5. Then BO is 0 is equal to 0. Substituting, we get the value. We get minus 20. It means because here we are giving to the inverting terminal, so we get the inverted output. So minus 3.125. After substitution, we get the value minus 3.125 voltage. Clear? Next one. Which type of switches are not preferable for simple weighted resistor type? So first one, bipolar transistors, B voltage switches, C MOSFET, D all of the mentioned. Here the answer option is A. Explanation, bipolar transistor does not perform well as voltage switches and MOSFET due to the inherent offset voltage when in saturation. Right. So this is the reason bipolar transistor not suitable for simple weighted resistors type digital to analog converters. Then seventh one, the inverted R2R ladder can also be operated in. Right, there are four options: inverted mode, current mode, voltage mode, non-inverted mode. Here the option is B. Explanation: the inverted mode R2R ladder circuit works on the principle of summing current. So therefore, it is said to be in current mode. Clear? Right. So next problem. The calculate the value of LSB and MSB of a 12-bit DAC for 10 volt. There are given options given four options. Here the answer is D is correct. Explanation: LSB is equal to 1 by 2 power n. So n value is at 12. So 1 by 2 power 12 is equal to 1 by 4, 4096. For 10 volt range, LSB is equal to 10 volt divided by 4096. It gives 2.4 millivolt. And the MSB is equal to 1 by 2 into full scale voltage. It gives 1 by 2 into 10, that is equal to 5. So option is D 2.4 volt, LSB 2.4 volt, MSB 5 volt. Then problem number 9. A 10-bit D2A converter have an output range from 0 to 9 volt. Calculate the output voltage produced when the input binary is 111 000 1010. The options are A plus or minus 7.96, B minus 7.96, C 7 plus 7.96, D none of the mentioned. Here the answer is C. Explanation: output voltage equation for 10-bit DTA converter. Output equation 9, VO is V into 1 divided by 1 plus 1 divided 1 into, for example, here we go 1 means 1 into 1 by 2, then 1 into 1 by 2 square plus 1 into 1 by 2 power 3. Then for 0 bit, 0 into 1 by 2 power 4, then 0 into 1 by 2 power 5, so and so on up to last bit 10 bit. So 0, well 0 into 0 it gives 0. We get 9 volt into 0.5 plus 0.25 plus 0 plus 1.125 plus 7.125 then 1 point into 10 power minus 3 plus 1.95 into 10 power minus 3, we get the value 7.96. So option is C. Then problem number 10. The basic step of 8-bit DAC is 12.4 millivolt. If the binary input is 000, 00000, totally 8 bits, represents a 0 volt. Determine the output if the input is 1011, 0111 value. Right, here options are 1.36 volt, B 2.27 volt, C 5.45 volt, D none of the mentioned. Option B, answer is B. Explanation: the output voltage for input signals 11011 equal to 12.4 millivolt into 1 into 2 power 7, but this is 7th bit, plus 0 into 2 power 6 plus 1 into 2 power 5 plus 1 into 2 power 4 plus 0 into 2 power 3 plus 1 into 2 power 2 plus 1 2 power 1 plus 1 into 2 power 0 equal to 12.4 into 128 plus 32 plus 16 plus 4 plus 2 plus 1. So we gives 12.4 millivolt into 183. It gives value 2.27. Next, number 11. How many control lines are present in analog to digital converter in addition to the reference voltage? So option 3, 2, 1, D none of the mentioned. Answer is B. Answer is 2. ADC usually has two additional control lines. That is one start input to tell start of conversion, that is SOC. Then second control signals, that is EOC, end of conversion. So these are the two control signals available in analog to digital converters. Then question number 12. The flash type A to D converters are also called as, right? The options are parallel non-inverting A to D converters, then B parallel counter A to D converters, C parallel inverting A to D converter, D parallel comparator A to D converter. Here the option is D. The flash type A to D converters are also called parallel comparator A to D converter because the purpose of the circuit is to compare the analog input voltage with each node voltage. So it is called parallel comparator A to D converters. Next, calculate the conversion time of 12-bit counter ADC, counter type ADC with 1 MHz clock frequent to convert full scale output. Options are 4.095 microseconds, 4.095 milliseconds, 4.095 seconds. Option one of the mentioned. Answer is B. Expression conversion time is equal to 2 power n minus 1 clock signals. So 2 power n here, here the 2 power n, 2 power n value 12 bits. So it gives the value 4.095 milliseconds. Question number 14. At what condition the digital to analog conversion is made? This example type. Here VA is greater than VD, VA is less than or equal to VD, then VA is greater than or equal to VD, VA is VA not equal to VD. Here the answer is B. Explanation: when VA is less than VD, the output of the comparator becomes low and the AND gate is disabled. So this stops the counting at the time, and the digital output of the counter represents the analog input voltage. So when VA is less than or equal to VD, the output of the gate comparator becomes low. Next, question number 15. In integrating type ADCs, there are 4 options which we have to find which one is correct. A input voltage is proportional to the input averaged over the integration period. Option B. output voltage is proportional to the input averaged over the integration period. C. Output voltage is proportional to the sum of input voltage. Option D. Input voltage is proportional to sum of input voltage. The correct answer is B. Because since integrating type ADCs do not require sample and hold circuit at the input. The change in input during conversion will not affect the output code and is proportional to the value of input averaged over the integration period. So the integrating type ADCs, the output voltage is proportional to the input averaged over the integration period. This is the explanation. Then question number 16. The dual slope has following specifications. Dual slope analog to digital converters. The 16-bit counter, clock rate is equal to 4 megahertz, input voltage is equal to 12 volt. If the output voltage is equal to -7 and the capacity is equal to 0.47 microfarad. If the counters have the cycled through 2 power n counts, determine the value of resistor in the integrator. There are 4 options given: 60 kilo ohms, 50 kilo ohms, 120 kilo ohms, then 100 kilo ohms. Here the answer is A. The explanation: time period for dual slope integrator del T is equal to T2 minus T1. Here the 2 power n counts divided by clock rate. So here 16-bit counter. So n naught n is equal to substitute 16 divided by 4 megahertz equal, it gives the value 16.38 milliseconds. For integration, del V naught is equal to minus 1 by RC into V into T2 minus T1. So it gives the value minus 12 volt divided by minus 7 volt into 16.38 milliseconds. It gives the value 28.08. So R value, it means 60 approximately for R is equal to 28.5 milliseconds, which is 59,744, approximately 60 kilo ohms. Then A is equal to 12-bit dual ramp generation has a maximum output voltage of 12 volt. Compute the equivalent digital number for the analog signal of plus 6 volt. Yeah, there are 4 options, right? 1, then 0, 0, 0, 0, 0, then 4 zeros. B 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Then C 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, then again 0, 0, 0. Then another option, this is the another one option, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Answer is D. How the, since VA is equal to formula, basic formula, VA is equal to VR into n divided by 2 power n. So digital count n is equal to 2 power n into VA by VR. The n is equal to n 2 power 12. It gives 6 divided by 12 volt. That is 4096 into 0.5. That is equal to 2048. So binary equivalent for 2048 is this value. So option is D. Right. Next, question number 18. Find out the resolution of 8-bit DAC and DADC circuits. Option 562, 625, C 256, D 265. So the 8-bit value. So n here n is equal to 2. Explanation: the results solution is the value of LSB resolution is equal to 2 power n, where n is equal to number of bits. So 2 power n is equal to 256 possible values. So answer is the C. Next, question number 19. How many equal intervals are present in a 14-bit D2A converters? There are 4 options: 16,383, 4,095, then 65,535, 1,023. So the simple explanation: a 14-bit D2A converter has a 2 power n minus 1 equal interval. Here n value is 14. So 2 power 14 is equal to 16,384. So minus 1, it gives 16,383. Clear? Next one. Find the resolution of a 10-bit A to D converter for an input range of 10 volt. Options 97.7 millivolt, 9.77 millivolt, 0.977 millivolt, 977 millivolt. Answer B. Resolution in volts VFS divided by 2 power n minus 1. VFS is equal to 10 volt full scale voltage, 10 voltage, 10 divided by 2 power 10 minus 1. So it gives 10 divided by 1023 equal to 9. 10 divided by 1023, it gives 9.77 voltage millivolt. Next question number, problem number 21. The time taken for output to settle within a specified band of its final value is referred as option A conversion time, option B settling time, C takeoff time, all of them mentioned. Here the answer is B. Settling time represents the time taken for output to settle time within a specific band plus or minus 1 by 2 LSB of its final value following a code change of the input, usually full scale voltage. So answer is the B, settling time. Then question number 22. A 4-bit R2R DAT converters has a reference of 10 volts. What is the analog voltage for an input code 0101? There are four options: 0.3125 voltage, 3.125 voltage, 0.78125 voltage, D minus 3.125 voltage. The option is B. The basic formula is full scale voltage 10 into then LSB value, MSB value 0 into 1 by 2 plus 1 into 1 by 4 plus 0 into 1 by 8 plus 1 into 1 by 16. So we get 3.125 voltage. So option B is the answer. Next question number 23. A binary weighted digital to analog converter has a input resistor of 100 kilo ohm. If the resistor is connected to a 5 volt source, the current through resistor is, they are asking the current through the resistance value. Yeah, very simple. We can use the Ohm's law formula. I is equal to V by R. They are given resistance value, voltage value. We have to calculate the current value. That's all. So basic formula I is equal to V by R. Here V is the 5, R is the 100K. So it gives the 50 microamps. So option is A. Sometimes they ask us this type of simple questions. Then 24th, a binary weighted digital to analog converter has a feedback resistor of RF of 12 kilo ohm. If 50 microamps of current through the resistor, the voltage voltage out of the circuit is, options are 0.6 voltage, minus 0.6, 0.1, minus 0.1. Here we take option. Here the option is B, minus 0.6 voltage. Because basic formula B, here they are given the resistance value and the current value. We have to calculate voltage value. So V is equal to I into R. So here we give the signals into the inverting terminal. So we put minus sign in front of the equation. So VO is equal to minus IO into RF. So minus 50 microampere into 12K. It gives minus 0.6 voltage. Then 25th problem. The resolution of a 0 to 5 voltage 6-bit DTA converter, a analog digital to analog converter is 63%, option B 64, option C 1.56, option D 15.6. Here answer is C. Resolution is equal to basic formula VFS is equal to divided by 2 per resolution equal to VFS divided by 2 per n minus 1. So VFS value equal to 5 divided by 2, n is equal to 6, 2 per 6 minus 1, we get 0.079. So in percentage 0.079 for 5 volt. So into we convert it to 100, we get 1.558. So approximately it is a 1.56. So another one, this is the example. in the digital to analog converter circuit, shown below, VR is equal to 10 volt and R is equal to 10 ohm. We have to find the current I, value, the value of I in this place, right? There are four options: 31.2 microamps, then 62.5 microamps, C 125 microamps, D 2250 microamps. Similarly, the voltage at VO output, we have to calculate the VO. There are four options: minus 7.878, minus 0.781 voltage, minus 1.562 voltage, C minus 3.125 voltage, D minus 6.25 voltage. Here we have to convert, design. For this, for one, it is connected to the reference signal. The zero, it is not connected. So here the V signal. Here this is the input current flow. Input current flowing path. In this path, the value is D2 divided I in by 2, because we have to apply the current divider. So half of the current going this path, remaining half the current going this path. So I in by 2. In this place, I in by 4. In this node, this is I in by 8. In this place, I in by 16. But we have to calculate the this current value. It is I in by 16, right? So similarly here also I in by 16 value, because it is two dividing, no, to current, using current divider rule. Here the two currents are split into equal parts. So I in by 16, here also I in by 16. Right, explanation, very simple. Due to virtual ground node at non-inverting terminal is considered as a ground. So input impedance is 10 kilo ohm. So I in is equal to 10 volt divided by 10k. It gives the value of 1 milliamps. Next, so I equal to I in by 16. In this place, I in by 16. So we get I is equal to I in by 16. Value of I in is equal to 1 milliamps. So 1 milliamps divided by 16, it gives the value of 62.5 microamps. Similarly, output voltage for the second question. The second output voltage is equal to minus R into I in by 4 plus I in by 16, because here these two signals are connected. This is not connected. This part is connected to the plus terminal. This part is connected to the plus terminal. So we get my VO is equal to minus R into I in by 4 plus I in by 16. Substitute the values of I in 62 point. This means 1 milliamps. 1 milliamps by 4 plus 1 milliamps by 16. Value of R. Then we get minus 3.125 voltage. Next, problem number 27. Right? So the DL slope ADC circuit uses a 16-bit counter and 4 MHz clock rate. The maximum input voltage is 10 volt. The maximum integrator output voltage should be minus 8 volt. When the counter has cycled through 2 power n counts, the capacitor is used in the integrator is 0.1 microfarad. Find the value of resistor R of the integrator. Very simple. Problem is the big one, but the solution is very simple. Time period is equal to T2 minus T1 in the DL slope converter. So it gives 2 power 16 divided by 4 megahertz. We get 16.38 milliseconds. For integrator, del V naught is equal to minus 1 by RC into VA into T2 minus T1. So RC is equal to minus 10 volt divided by minus 8 volt into 16.3 milliseconds. We get the value 20.47 milliseconds. R is equal to 20.47 milliseconds divided by 0.1 microfarad. We get the value 204.7. Approximately it is a 205 kilo ohms. Next, problem number 28. Consider a 4-bit DAC circuit. The analog value corresponding to a digital signals of values 000 to 0001 or 0 volt and 0.0625 volt respectively. The analog voltage in volts corresponding to digital signals 1111 is, they are asking for 15 volt signals. Simply we have to multiply the 4-bit value 0.0625. For example, 0 for 4 zeros output voltage is equal to 0. For 0001 next to the value we are getting 0.065. That means for one signal, for one input, for one we get 0.065 voltage. The analog voltage for 0001, the decimal value is 1. Similarly, for 1111, decimal value is 15. Is it right? Hexadecimal value is 15. So 15 into 0.0625, it gives the value of 0.9375. Well, we get the value, this value. This is the for 15. Clear? Next, problem number 29. For a given S and H circuit, if the value of hold capacitor is increased, then dupe rate decreases with the acquisition time decreases. Dupe rate decreases and acquisition time increases. Dupe rate increases and acquisition time decreases. Dupe rate increases and acquisition time increases. Here the answer is B. In capacitor, we know that in capacitor I is equal to C into dV by dt. Right? So dV by dt is directly proportional to 1 by C. dV by dt is directly proportional to 1 by C. Here the charge Q is equal to C into V. It is I into T value, amount of current into time. So T is equal to CB divided by I. CB is divided by I. So here the T is directly proportional to C. Timing is directly proportional to capacitance of a capacitor. From the above relation, it is clear that if the C value increases, acquisition time also increases as a proportional relation. So the answer is B. Question number 30. An 8-bit DAC accepts an input voltage signal range from 0 to 12 volt. What is the digital output form for an input voltage of 6 volt? So these are options given: 10000, then 00002, then option B, C, and D. We have to convert the values. The n is equal to 8, VFS is equal to 12 volt. N number of bits, that is 8 value, VFS value 12 volt. Resolution is equal to 2 power n, n is equal to 2 power n. So n naught value 2, 2 power 8 is equal to 256. Resolution VFS divided by 2 power n minus 1. So 12 divided by 2 power n minus 1, it gives 0.047. So digital value, digital output is equal to 6 volt divided by 0.047, that is equal to, it gives 128. So binary equivalent of this 128 is 10000000. So the option is A is the answer. Thank you. Thank you for your listening in this class. I think I have given a brief introduction about the analog to digital conversions and digital to analog converters, basic technique methods, types of circuits, then sample and hold circuit, and example problems to you. Right? Please utilize this. Thank you. Thank you for listening. Thank you to department. Thank you to our college, Erode Sengunthar Engineering College. Then pre-runner scheme AICTE. Thank you. Thank you.